Okay, well, welcome everybody to this edition of HIT seminar. Today, we are very glad to have Mark Lisa to give this talk. And I assume everybody knows Mark from here, but let me just still give him a brief introduction. Mike got his PhD from Michigan State University in 1993. And then immediately after that, he was a postdoc at Berkeley from 93 to 96. And then from 96 on, he went to Ohio State University, and then currently is a full professor over there. Mike was elected to APS Fellow in 2004. And then a fellow of American Association for Advancement of Science in 2021. And he was awarded as Ohio State University Distinguished Scholar in 2020. And then in the same year, he got also a Fulbright Scholarship in 2020. That's where he's speaking from today, in Brazil. So he will talk about subatomic smoke rings, polarization, and toroidal vorticity in the QGP. Mike, please take it away.
Okay, good. So thanks for telling me this was a 2-hour seminar, so that's great.
Oh, no, this.
Okay.
This is
anyway, thanks for inviting me. I guess the last time I was there was called the Heavy Ion T. I see it's changed its name. Let's see if I can get.
No, it didn't, Mike. You changed your transparency.
What do you mean? It's on the website. It says Hadron Ion T, formerly Heavy Ion T. Got to keep with it, Gratian. Okay, here's my outline. I'm going to give just a little motivation and review of hyperon polarization. I think that that's probably not necessary, but nevertheless, I don't like to start a seminar from standstill, let's say. Then I'm going to talk about structures, toroidal vortex structures at forward rapidity and AA collisions, and then talk about PA collisions and jets moving through a QGP. In both of those cases, I'll make the case that we have something small, a small thing blasting through a big thing and setting up unique geometry that we can measure. And then I'll summarize. Let's see. These are my collaborators on what we've called ourselves the 3C collaboration, and they've co-authored the papers with me. So as sort of a reminder of something that we all know, key to our understanding, we're trying to get physics information from the data at RHIC in our standard model of heavy ion collisions is viscous hydrodynamics. That's what we think gives us the tools to go from a set of equations, which are basically conservation laws and transport coefficients, to try to get a handle on the equation of state. And we do this by studying the fluid itself as it's calculated and as it evolves. Now, of course, what I measure is not a fluid, but we can focus on the fluid cells, and we'd like to understand those by measuring the hadrons in the detector. So that's the idea. We'd like to get a sense of what's going on at the fluid cell level so we can understand its evolution through hydrodynamics, and then maybe say something at some point about the equation of state. I'm going to see if I can turn that into a pointer. Hopefully I don't just screw this all up here. There we go. Good, maybe that's a little better. Good. Well, we don't really know what drives freeze out in detail. Nevertheless, we often will work with Cooper-Frye formalism where really we're driven by conservation laws and just sampling the fluid to extract hadrons from within them. So we measure the particles and we hope to get a sense of the properties of the parent fluid cells. So in particular, if I think in terms of fluid properties, I might be talking about the chemical potential, the baryochemical, electrochemical potential, whatever it is, and the temperature of the fluid in the cell. And for the hadrons, that means I'm looking at yields, basically, the yields as a function of flavor or whatever else. And this is an old plot, and the updates to these old plots look pretty much the same as the old plots. So I'll just point out that whether or not a strictly thermodynamic picture is warranted, it seems to do quite well for explaining particle ratios and large number of particle ratios. So this tells us something about chemical potentials and temperatures. We can go into more detail than just yields by looking at the distributions of particles. And just like we saw a equilibrium model doing a fair job in terms of overall yields, hydrodynamic, the equilibrium hydrodynamics going through Cooper-Frye does a good job of reproducing the longitudinal degrees of freedom as well as the transverse degrees of freedom, basically the longitudinal and transverse momentum spectra. Likewise, as we know, we can look in more detail at the anisotropy of the momentum spectra. This gets into even more detail. We know we have these moments about the azimuthal direction around the beam, V2, V3, V4, ever more complicated modes or more detailed modes of the system as it freezes out. And we see again that hydrodynamics does an excellent job, especially at the highest energies where viscosity is more under control, of reproducing V2, V3, V4, etc. as a function of dt. So what we've found over the years, and this is not doing it all justice, is that hydrodynamics is a good model for connecting the initial fluid, as far as we know, to the hadrons that we measure at the end. So we think we're measuring things like chemical potential, temperature, and collective velocity by taking a look at the flavors and yields and the momenta. That gets us to finer and finer detail. Now the question is, what more can we do? We'll look at non-central collisions. That's often what's most interesting anyway. And one thing that we will pay attention to, and that at least until about 5-6 years ago, the angular momentum of the system, while it's on the order of 10,000 h-bar, really hasn't gotten the attention it deserves. A little bit of V1, but not much else. We know in this collision that the initial angular momentum points into the screen, I guess. But the question is, how is that distributed at the end? And what's the consequence of that? If I take a look sort of at the naive view, I just drew these arrows on by hand, of some kind of initial shear, it's pretty clear there's angular momentum associated with the fluid if it's represented, I guess, by that shear field. There is a vorticity, in other words, just, if I think non-relativistically, the curl of the flow field. And probably these little vortices themselves move. They're going to be distributed somehow. They themselves are going to move, but that'll be a feature of the fluid cell, which now has a rotational aspect to it. And we can take a look at, more complicated situations. This is a numerical simulation of galaxies that one of my colleagues pointed me to, and I thought that was just pretty cool. I mean, if you take a look at the upper left, these two fellows are coming towards each other. When they, after they pass through each other, the residual galaxies, that's what these are, have less angular momentum associated with the center of mass motion of the galaxies themselves. Some of it has been transferred to the rotational motion of each galaxy and perhaps to vorticity of the intervening gas. That's the sort of thing we would love to get the details of. And there we're measuring, in that case, the vorticity of the fluid. That's having a lot more detail than simply the collective motion of the fluid. And that we get by measuring the polarization of the hadrons that come out. So at least in very crude terms, the probability, I should pay attention over here, the probability to measure a hadron depends on, well, the temperature of the system. It depends on the hadron's baryon number times the hadrochemical potential, times the charge of the hadron, times the charge chemical potential, and then the spin of the hadron dotted with the vorticity. So the vorticity is, in a sense, the spin chemical potential. That's how we'd like to make a connection between the hadrons and the fluid itself. And this is not actually the first observation of a mechanical rotation of the fluid, which is to say the vorticity, coupling to the spin, the quantum spin of an object inside the fluid. The first observation was by Takahashi, where we had liquid flowing through a channel, and just due to the friction, on the walls, we would have slower fluid on the sides, faster fluid in the middle. that would lead to a natural vorticity field like the shear that I showed you just a minute ago. And the point is that vorticity gets transferred to the electrons, actually to the atoms that make up the fluid, which I believe in this case is mercury. So I'll have some sort of gradient of vorticity as I go across this channel here. That makes sense. And one can then measure the so-called spin, well, the spin gradient across the channel itself, as here the fluid is flowing towards us. And that can be measured by a so-called spin voltage, and I really don't even know much about it except to say that it can be measured. And in fact, this very formula that the probability of measuring a particular spin is given by the vorticity of the fluid, dotted with the spin itself, divided by KT. That's in Takahashi's paper, just like it's in ours. Now, in his case, he's able to see the vorticity, measure this spin voltage, and he can verify this relationship. We use that relationship. We are the second observation of fluid vorticity leading to a spin coupling, quantum spin coupling. And in fact, it was only made 1 year later, or published really 1 year later, also in Nature. So that was kind of interesting. So we know for the data that was published in Nature, as well as some other data plotted here, that we have this global polarization, which is quantified, let's see, where's my pointer? Quantified by a the spin of the lambdas dotted in the direction of the angular momentum of the system. I won't go through the mechanics of how we measure the angular momentum direction of the system through the reaction plane and so forth, at least for this audience. But we measured the polarization as a function of energy in the system. And while the angular momentum of the system goes up with energy naturally for a fixed impact parameter, the polarization itself goes down. And that's what's plotted with the color points from Starr and by Alice. And what's interesting is actually that hydrodynamic calculations, many of these existed before, and they predicted this polarization as a function of root S. That's important because global polarization had not been measured before, or at least it had been claimed to be zero with large error bars. So this tells me, or at least suggests to me, that lambda polarization is a well understood and calibrated tool to access the fluid substructure. Now you could say so far, well, it just predicted or just confirmed what we knew already without even knowing that we knew it from hydrodynamics. Well, things get more interesting later. The main thing is we seem to be on the right track. We can make a connection between the vorticity and the hydrodynamics, going through the Cooper-Frye, and connecting it to the hyperons that we measure at the end. Okay? And this is true not only for lambdas, but also for cascade and omega baryons, so heavier hyperons with more strangeness. Here, of course, the error bars are larger because the statistics are smaller and so forth. But we see that lambdas and cascades are within error bars consistent with the lambda hyperons. So we seem to have, at least in the baryon sector, the mesons seem to be quite different. A common fluid vorticity that can explain all the hyperons. So much for the global polarization, which is what I was talking about, the angular momentum or the alignment of the hyperon spins with the global angular momentum of the system that's shown here on the left. We also have other directions, for example, in the longitudinal direction. So on the right-hand side, the beam is coming towards us. It's a non-central collision, so we have the familiar ellipse shape. And just like before, where I drew these arrows, which we know must be there, these black arrows, we know we have elliptic flow. So we have stronger flow left and right in the reaction plane than out of the reaction plane. And this leads, if I just think about the curl of the flow field, and non-relativistically and naively, the vorticity should be the curl of the flow field, it leads to vorticity that alternates as a function of quadrant. So first it should be positive and then negative as I go in phi, positive and then negative again. That's what one might expect. And in fact, that is indeed what was seen by Starr and then later by Alice. This is something that's basically proportional to this longitudinal polarization, the polarization that points towards you. It's positive and then goes negative as we cross quadrants. And in fact, this little picture here, this naive blast wave picture does seem to agree with the data quantitatively. On the other hand, that is just a cartoon picture. And if I would say, what does hydrodynamics say? Well, that's given here by the red points, okay? That's the vorticity, the so-called thermal vorticity. So there are different flavors of vorticity that one can define. Non-relativistically, it's the curl. Okay, if I go relativistically, of course, I have to take four-dimensional derivatives of four velocities and so forth. So the natural, naive generalization of the 3D curl is the so-called kinematic vorticity, the first one listed here. But Beccattini has long made an argument that really it's not only the flow velocity that matters, but also temperature gradients. Temperature, of course, can also depend on position. So one should use the so-called thermal vorticity, and that's what most groups do. In fact, I would say that's what all groups do. But for a short time, first of all, that doesn't seem to work, does it? It has the wrong magnitude and certainly the wrong sign of the oscillation. What was pointed out was one could define a so-called T-vorticity, where the quantity that you take in this antisymmetric derivative of is not mu or u over temperature, but it's temperature times u. And the justification for this is obscure, and I would say it's not well justified, except to say that it seems to work. On the other hand, a lot more has been learned since, well, even more recently. There are more contributions than simply curls to the polarization. And I won't go much into detail. That's shown down here in these two papers, or described down here in these two papers, that there should be an additional term, a so-called shear-induced polarization, which is given in terms of, well, shear tensors as well as the momentum of the particles dotted with either the time direction, which is the Beccattini formalism, BPP given here, or the flow velocity or the velocity direction as proposed by Liu and Yin, or I think Liu and Yin, actually, I'm sorry. Up on top here is a calculation by Chun Shen using these two flavors, I guess, of shear-induced polarization. And what you see, if I just use thermal vorticity, that's the black curve, totally gets the sign wrong and the amplitude wrong. If I use the LY shear-induced polarization, I see that it gets closer to the truth. Still have the wrong sign, however. If one would use, instead of the lambda hyperon mass in the Cooper-Frye freeze-out, the strange quark mass, you can flip the sign. On the other hand, the amplitude is wrong and many other things become wrong. The point is, these terms can help go in the right direction. And as a matter of fact, Beccattini's term, which is shown by the red line in Chun's calculation, reproduces the data well. So we may be learning more about what in hydrodynamics, what gradients affect the measurables that we see. So that's one reason it becomes more interesting. Now, I really don't want to talk about global or hyperon polarization or longitudinal polarization. I want to talk about other things. So let me talk about central gold or lead or whatever it is collisions. Now, in the upper left-hand plot, there's angular momentum in the system, obviously. In the upper right-hand plot, that's a non-central collision, so there's angular momentum there too. If I have a central collision between identical smooth nuclei, for example, there's no angular momentum of any type in the system. Nevertheless, there are flow fields and gradients and curls of flow fields. So naively, a central collision should have, and does have, more radial flow, transverse flow at mid-rapidity than at forward rapidity. And that means if I take a curl, just to get a picture, I will have a vorticity at various points in the system. And if I just take a look at forward rapidity on the right-hand side here, you can imagine the symmetry as it goes out of the page. I here have a ring of vorticity, and I can show that here on the right in this nice paper by Jia et al. I have vorticity that is going in a ring about the z-axis. Nothing is spinning about the z-axis. This is basically a smoke ring. So in this case, I guess I'll point up at the top, in the upper left, the vorticity is along the direction of the total angular momentum, On the right, the vorticity is in and out of the screen. And on the bottom, the vorticity is perpendicular or parallel rather to the z direction crossed with the momentum of the lambda. It's more complicated. This has been predicted. This is a calculation, a nice paper by Xie et al. This is now the vorticity vectors in the forward pseudo-rapidity and the backward pseudo-rapidity. One can quantify that, well, as little arrows on a graph, but you can quantify it maybe a little better by taking the vorticity and dotting it with the direction of that the vorticity in the smoke ring would go. So now you have a nice scalar factor. One can generalize that to 4 dimensions and have something that we call R sub fluid. So you'll see that sometimes. In the music hydrodynamic code by Shen et al., one can calculate this ring vorticity, so to say. So this is now going to be goal-goal collisions. The right-hand panel is forward pseudo-rapidity. The left-hand panel is backward pseudo-rapidity. This is in space-time, so this is space-time rapidity. And in the middle, we'll see the system from the top, so to say. And you can see the evolution of the system. We have a transverse flow shown by the green arrows, and we saw vorticity shown by black arrows. I think I'm going to show it again and let it evolve. And you can see that there's a nice vorticity that's, I don't know how well my screen is showing up, is going clockwise on the right and counterclockwise on the left. And that quantity that I showed you, that scalar quantity, is what's shown in the colors, okay? Basically, we see that it's negative in the forward direction, positive in the backward direction, anti-symmetric around mid-rapidity, as it must be. Okay. This has actually been predicted at all energies. So at the very lowest energies, well before we came along, at the lowest energies, like preparing for Nika, for example, in 2015, 2016, a lot of Russian calculations using transport models as well as 3-fluid hydrodynamics predicted these so-called femto tornadoes, as they called them at some point. So that's down at fixed target energies. They've also been predicted, again, by a Russian group in beam energy scan energies, and also, as I showed you just a moment ago, by Xie et al. At RHIC and LHC energies. So again, these are central collisions. It also happens in non-central collisions, but I'm showing you central just to indicate that this has nothing to do with non-central collisions necessarily, that you'll have these forward and backward ring vorticity patterns. Now, they can be measured in Hades and star fixed target and so forth, because they're mostly at forward rapidities. And in fixed target, we can measure this. At star, without forward tracking upgrades, that becomes very hard. And the same is true for, Alice and so forth at the LHC. A good place that can measure these ring structures, and again, these are AA collisions, is LHCb. Because you don't need a reaction plane or anything for this. All you need is forward rapidity and the ability to measure lambda hyperons. And LHCb should be able to measure these structures. It really would be a unique discovery, and I would say this would be a compelling demonstration of really fluid behavior at the forward rapidity extreme. And we've talked to the LHCb people, and I think they're on it. There are other symmetries. So I showed you the top 3 symmetries of measuring polarization. There are other symmetries like at the lower left. This now, for example, is a jet passing through a fluid. I don't know, maybe a quark law in plasma, maybe it's not. Maybe it's not a fluid at all. But let's assume that I have a fluid and I have a hard particle, which is to say a fast particle, blasting its way through. This was proposed first, well, I don't know about first, I think it was first by Betts, Galassi, and Torrieri in one of their papers. It's been written by many folks, and now as well by us, where you say there as well will be a ring structure. If I take a look in the lower left, you see that I'll get on top of the jet, which is passing to the right, on top, so to speak, a vorticity pointing out of the page. On the bottom, it's pointing into the page. And if I go around the jet, I'll have a ring, not around the z-axis, but around the jet direction. And that's what I'm trying to indicate here with this little smoke ring structure. Okay. We've published this, and this is a little calculation, again, a little movie of this structure as a jet passes through the corpuscle and plasma. This is calculated with the music hydrocode. And on the left-hand panel, the jet is moving to the right, and you can see naturally the curl of the flow field and this ring vorticity scalar thing that I showed you before, shown in red and blue. Likewise, on the right, I'm going to make it play again, I think. On the right, the jet is coming out towards you, and you can see that there's a vorticity structure that sets up around the jet direction. This can be measured and quantified, and we've given this little quantity here, this ring scalar here, which depends on the axis, and in this case, the T hat would be the jet direction. And there's some predictions here using the music hydrodynamic code of this scalar quantity as a function of angle about the beam axis, or about the jet direction, I should say. I won't go into details, the paper's down here, except to say that this is actually highly sensitive to the viscosity of the surrounding medium. Not a shocking statement, since viscosity tends to kill local vorticity and turns it into a larger circulation. I want to move on now kind of to the main point of what I wanted to talk about, and that's proton A collisions. Here, everything up until now has been heavy ions, but in proton gold or proton lead collisions, there's the claim that the smallest droplet of QGP has been formed. And as mostly is the case when one's talking about hydroproofs, we're looking at V2, V3, V4, etc. That's almost always what we're looking at. So on the right-hand side, we can see V2 for PP collisions, and then for P-lead and then lead-lead collisions at the LHC. For the PP, we see that the two-particle cumulant gives the same as the multi-particle cumulant, suggesting that we really don't have multiple particles. It's not really true flow. This can be argued, but nevertheless, there's not a strong case for flow in PP, at least in this picture, whereas in P-lead and lead-lead, we do see true multi-particle flow, in this case V2. On the bottom right, we see the V2 measured by Phoenix from proton gold, deuteron gold, and helion gold. And if one initiates the hydrocode with geometries which may be represented by proton, deuteron, and helion gold, the hydrodynamics actually reproduces the V2 amazingly well as a function of PT. So it really suggests that it is the smallest droplet of QGP, or at least fluid. On the other hand, at least speaking for myself, basing everything on V sub n gets a little bit much. It seems to prove that hydrodynamics works maybe even everywhere, maybe even in PP. I said this could be argued, but I don't want to argue it. I'd like to look at things from a different point of view. And it was Urs Wiedemann who always made this statement to me, that every time you break a symmetry, you learn something. So I want to learn something. Instead of only looking at AA collisions, I want to take a look at proton gold collisions and specifically pay attention to the forward-backward structure. Maybe something interesting can happen. So let's assume that I have a proton gold collision and a fluid is created. Maybe it is, maybe it's not, I don't know. The default sort of scenario would be that it's basically like a small heavy ion collision, at least in the region where the proton and the gold overlap. So the longitudinal flow profile would be Bjorkane flow. It would basically be that the space-time rapidity is the same as the momentum space rapidity. Naturally, there's more stuff going in the gold direction than the proton direction, so that would be shifted. You can see with these little arrows here that more are pointing backwards than forwards. Nevertheless, this would be the flow profile that one might assume, and usually does assume. I would argue that might be a little bit naive, that, you know, the reason we have vorticity in the non-central collisions, for example, is that there's sort of a drag of the leftward going nucleus on the rightward going nucleus, just to speak grossly. And in such a picture as the proton gold, I would kind of expect a drag towards the gold direction on the edge of our little quark-gluon plasma. The proton is coming blasting through towards us. And I would think it's natural to expect the outer edge, let's say, of the quark-gluon plasma to be moving in the gold direction, and the inner region, I guess, to be moving towards us, at least in some frame, not just having the same longitudinal flow independent of transverse direction. We put these two scenarios into music, and we find that the larger, the things that you would look for at first for a calculation from a hydrocode seem to be rather invariant, independent of this initial state. I get the same, for example, dn, d eta from scenario A and scenario B. I would like to pause to make sure that people are still there.
Yes, we're here.
Thank you, Peter. Okay, you're leaving me hanging there. Very good. Okay, so it looks like we have the same, basic things that we would measure regardless of these two profiles. So just taking a look at the dn d eta, as Yuri Kovtchikov first suggested to me, will not distinguish these two. What will distinguish them? Well, the vorticity will. You can see on the right-hand side, we do have these little curls, at least if I think in terms of non-relativistic curl. And that would be basically smoke rings or a smoke tube. As a matter of fact, talking about the geometry, I told you, and it's often shown in talks, that fluid is flowing down some kind of channel and rubbing against the walls and so forth. And that's in their paper. But the real geometry of that experiment was fluid flowing through a tube, a small capillary, where again, you have vorticity due to the drag on the walls of the tube. And in fact, you have a toroidal vorticity configuration, just like I'm claiming that one would expect in a PA collision or might expect. So now we have a fifth, I believe, that is geometry, where one could take a look for vorticity. This time it is small stuff blasting through big stuff, but now in the beam direction. That's actually a lot easier than the jet stuff. Let me show you our movies again. The colors are again going to be given by this scalar product. I always show it to myself non-relativistically first because I get lost in the indices, but this is then the relativistic generalization of our scalar product of the toroidal vorticity pattern. I'm showing the vorticity itself as red arrows and the collective velocity is green. In scenario A, it looks a lot like a heavy ion collision. I have blue in the front and red on the back. I'm going to play it again. It goes real fast. And we see that the system starts off with no vorticity. It quickly picks it up for the same reason that central AA does, and it looks kind of like a central AA collision. Whereas in scenario B, it's quite different. In this case, I have a positive ring vorticity according to the sign convention that we're using. The vorticity is going in the counterclockwise direction at forward and mid and backward rapidity. Quite different signature. These are just some sort of snapshots. This is of fluid, not lambda hyperons. On the top, we're looking at the central gold, which I showed you before, and the bottom two are snapshots of the two evolutions for the PP. You can see that the normal Bjorkane resembles quite a bit an AA collision, of course, shifted over to the left because the gold is going to the left. So I'd like to go from just looking at fluid to lambda hyperon. So this little swimming pool picture is kind of just cute, but I like it because the kid puts a ball into it. So you can see that the fluid has some structure, and by catching onto the ball, that's our hyperon, we can see how it's spinning and get a sense of what is the fluid vorticity structure. But okay, we don't have to keep looking at that all the time. The way we make the connection, as I said at the beginning, as a matter of fact, is through the Cooper-Frye formalism. This is the Cooper-Frye formalism for spin. It tells us that the spin field that we would expect is related to the vorticity in the fluid. That's this omega tensor here. And then we're freezing out over some hypersurface sigma. And then, of course, there's the parade of Greek superscripts that come in between. But anyway, it tells me how to connect the fluid to the particle. And as I said before, there's always the question, what flavor of vorticity are you using, and what flavor, if any, of symmetric shear contributions are you going to use? So I'm going to show you these as well. So I just thought I'd remind you of that. Well, we can form not just fluid vorticity R quantities, but also the lambda R quantities. In other words, this is what the experimentalists should be able to measure, okay? We can take a look at the spin orientation of the lambdas, dot that with the beam direction, C, and the lambda momentum, P. We measure all those things. We could take a triple product, and that gives us our ring vorticity measure that we'll measure. I'm taking a look at scenario A and scenario B here, the Bjorkane flow profile and the more natural, I would claim, profile shown in red and blue. For gold, naturally, they're the same. For pre-gold, well, in fact, they are quite different. You're not surprised by that based on the movies I just showed you. But if we have this smoke tube situation, which I would argue is natural, we get a strong signal at mid-rapidity for proton gold collisions. This is true whether we're using kinetic or thermal or T vorticity. Thermal is the correct one to use. And we would expect something like a 4% effect here. It's true for hyperons and for anti-hyperons. The reason there's any difference at all, by the way, is that this music hydrodynamics does conserve baryon number. And of course, baryons and anti-baryons, we have a finite baryochemical potential. So lambdas and anti-lambdas are going to be different. If I take a look at LHC energies, now I've added that on the right, we see in fact that yes, indeed, there is this signal, but it has flipped sign. The reason I point that out is that this is not so trivial. That little movie that I showed you might have made it look trivial, but this ring quantity actually rises, and around RHIC energies, where it might freeze out around 2 Fermi over C or so, we expect a positive number, but then it can turn around when we go to very high energies, or we don't look at proton gold, but instead, let's say, oxygen gold, and it lives a little longer. So the point is, it is complicated. Nevertheless, there's a clear signal there. Everything I've shown you so far has been for smooth initial conditions. What happens when we go to lumpy initial conditions? And then, of course, we have to run hydro over and over again and sample lumpy initial conditions. The answer is that not much changes, at least quantitatively, or certainly not qualitatively and even quantitatively. This is the same as what we looked at before. This is proton gold. That's what I showed you before. We've also done the calculation for helium gold and carbon gold, oxygen, etc. Not surprisingly, as I get more symmetric, the signal goes down. But this is true for all these lumpy initial conditions, and I find that rather comforting to see that this should be a robust signal. One can, okay, I'll mention this. One can say that reality might be lying between these two scenarios. It almost always is, isn't it? And we can quantify this with this so-called F parameter. So if F is equal to 0, that corresponds to Bjorkane flow, what the natural, or I wouldn't actually say natural, it would be your first guess of what the flow profile would look like. F equals 1 is what I would think the natural profile would look like. And you can see that there's a very clear difference. The scale is different on all these plots. There's some argument that at RHIC, F might be on the order of 15%. I actually don't know if I totally believe that argument, but nevertheless, let's say it's 15%, you still have a strong signal to look at on the order of 1% or so. Good. These shear terms that I told you about come into play in a big way. They made a big effect in the longitudinal polarization, not a really big effect in terms of global polarization, some, but not a big one. But on this smoke ring polarization, the toroidal polarization, they play they have a large effect going from black to the green and blue, or more dramatically, when going to Francesco Beccattini's formulation of the shear term, this red curve, I would say it's not intuitive what's going on with these shear terms. It's certainly non-trivial. Nevertheless, you expect a large signal at mid-rapidity even with the shear term. So it'll be interesting to sort of map this out and see what we can see in terms of the eta dependence of this thing. Good. I'm trying to say that it would be very interesting to measure. I'd also like to mention that it'll be pretty hard to measure. And this discussion can get kind of involved even for experimentalists, except all I will say is that the decay topology of a hyperon depends on the spin direction of the hyperon, which is actually how we measure the spin of the hyperon in the first place. However, the detector acceptance effects also depend on the decay topology of that hyperon. The point being, if I take a system in which there is certainly no toroidal vorticity pattern at mid-rapidity, for example, AA collisions, and I make this measurement, I will see a huge signal, and it's purely from detector effects. The first one to notice this was Sergei Voloshin, as a matter of fact, and we see it also in simulations and in the data. It's a large effect. It's not a simple effect. If it was small or simple, I might say, let's do a detector simulation and correct for the effect. If something's big, like 10 times as big as the signal of interest, and highly non-trivial, I don't know if I trust STARS or any other experiment's simulation well enough to correct for it, especially when I'm trying to say I've found a new, never seen before configuration. The only way to get rid of this effect is to take a measurement with one field direction in a solenoidal detector like STAR and ALICE, and then measure the same thing again after having flipped the magnetic field of the detector. Then the effects legitimately cancel out. And Joey Adams will be giving a talk on this at Brookhaven. The reason we're pushing that is because RHIC will close rather soon, and we have to take this measurement. We have a unique opportunity which is not lasting forever. An advantage of the, so that's sort of the challenges for measuring this thing. The advantage of measuring a 1% signal in the topology decay of a lambda hyperon is, for this, you don't need a reaction plane. You don't need an event plane at all. You're looking around the beam direction, which we know that pretty well. If I have a reaction plane resolution on the order of, let's say, 0.3 or so, I am still able to measure a 1% effect. That's what's shown by the upper plot here, after all. It should be then easy, with similar statistics, to measure a 1% effect with the ring polarization. So I would argue that we should do that. This is my summary, that AA and PA collisions do generate complex flow, and that flow can be probed by vorticity at the finest scale, much more fine than V2 or something like that. It's interesting that we could take a look at central heavy ion, and it could also be light ion collisions at all energies and find a circular vorticity pattern, and LHCb should get on it and make that discovery. I would say that we took a look at small things blasting through big things, that's jets, but I focused more on PA system where I would naturally, I would say, generate a vortical toroid configuration even in the initial state. And this would be, I would think, more compelling than V2 evidence for hydronature of these maybe smallest droplets of QGP. I've given you an experimentally important observable R quantity. It has a different symmetry than so-called production plane polarization, which I could talk about later if we want to. It's a few percent effect, which can be measured with a dedicated runtime at RHIC, and I hope we do this while we can. And those are my collaborators at the bottom. And you're still there, Peter?
I am, yeah. I'm wondering whether Shinyan is there. He's not only the chair, but he may have disappeared, in which case I will take over the function of chair. Thanks, Mike. Is fascinating. Very, very clear and provocative calculation. So questions for Mike?
Well, I'm still here. Maybe I do have a question. Can you hear me?
Yeah, sure.
Yeah. I'm sorry. I'm on the phone actually listening. What is from your hydro simulation, the signal you're talking about on average? What is the fraction of multiplicity you're talking about? Number of particles. Because from our simulation, the medium induced, what we call medium induced part of particle, their number are really small.
Okay, I'm afraid I don't understand the question.
Oh, the question is that you're talking about.
I think we may have lost Shinyan. Shinyan, you there? Shinyan?
Was the question the number of particles participating in the vortex?
Yeah, I think that was.
Okay, the number of particles participating in the vortex. I don't think that's a well-defined question. I mean, fluid has vorticity. I think it really does. It really is important to make the distinction between fluid and particle, and the veil, the curtain, is the Cooper-Frye formalism. So it's not so much that particles participate in a vortex or something like that. The vortex, the fluid has vorticity. A given fluid cell has an angular momentum structure to it. It has a curl of the flow field. That's a local quantity. And the properties of a fluid cell, when it freezes out, get reflected in the particles that were emitted from that cell. That's true for PT spectra, longitudinal spectra, yields, and everything. So I think that's the answer I have. I mean,
Yes. Yeah. Maybe I understand. Maybe what you talk about is what you talk about is probably the MPA. You're talking about, there is a vorticity over there. What I actually trying to find out from your simulation, because you did this calculation of smoke ring induced by jet, right?
yes.
And that depends on that signal only, is there the induced part, there's a lot of fluid, and you only look at the particles coming from the medium response, and those number of particles are, to me, they're small number,
So let's see. I'm not sure that I understand too much else. So you're saying that the particles coming from the medium, you say, is a small number.
Response.
Okay.
Yeah. If you look at induced by jet, if you think about jet going through the medium, and then it's sort of like a medium response, right?
Yeah. But we're not only. I'm sorry. Let me let you finish.
Yeah, maybe you are not talking about this, maybe, but I do remember you have a paper on that, right?
Yeah.
So
Yeah.
Mike, I in fact had a question on exactly the same point. Could you put up your slide where you've got the jet with the smoke ring?
Yeah.
Basically the same question as Shinyan, but I think the figure would help.
Good. This one.
I'm not seeing things move here. There we go. Yeah, there we go. Okay. So right. So in the bottom left box and the jet and the very nice graphics. So if I think experimentally, if I'm looking at what you call a partially quenched jet, I do some clustering to get rid of my backgrounds. I do all my magic, and I get energy momentum flow associated with what I want to call a jet, say a 20 G jet. It would be a very reasonable thing. Now, in fact, your figure is already good from the point I think you and I want to ask, namely, a jet originates with a very high Q squared object that then evolves, fragments, and radiates into a shower and eventually fragments into hadrons. And those come from the breakup of the high Q squared object. At the same time, it's interacting with the medium the medium picks up energy momentum from the jet,
Yeah.
and kind of develops a flow in the direction of the jet.
Right.
And it seems to me only that second. So that's theoretically one can distinguish, experimentally not. It seems
We're not.
it seems that second component is the only one that will pick up the vorticity from this process, but experimentally, pions do not come labeled, from the medium or from the jet fragmentation. I think even in principle, it's
Neither,
distinguished.
yeah, neither do they become labeled from music. I mean, we're not looking, first of all, we're not looking at the fragments of the jet or something like that. I mean, this is all from the medium, and there's no like the particles that are coming from the medium response and the particles that are in the medium and don't respond or something like that. I mean, this is all the lambdas, all of them. They're not.
They're going to be lambdas from the jet fragmentation. Which
No.
Why not?
I'm sorry. Go ahead.
What happens to them?
The lambdas from the jet fragmentation?
Yeah.
No, there's no fragmentation here. This is pure medium, but we're looking at.
Not following. I mean, experimentally, a jet breaks up into hadrons, some of which are lambdas.
Right. And
they will be detected along with everything else.
Yes, and they'll be, that's true. Yeah, I mean, so we're not looking at lambdas that are coming from fragmentation.
I understand what you're calculating. I'm just acting operationally in an experiment. These will not be distinguishable. I'm not doubting your calculation. I'm only saying that this effect will be diluted to diluted, not diluted,
Right.
diluted to the extent that there are lambdas coming from kind of non-fluid sources, which
Sure.
one cannot, I think, discriminate experimentally in any way.
That's fine. It's a question of where most of these particles are. I mean, we're looking at low PT. This figure here on the right, I guess, is for less than 3 GeV. But, I probably would have made that figure for less than 1 GeV or less than 500 MeV. We want to look just at the medium. And then fragmentation jets will get in there too, but they're not going to dominate the yield. I mean, no way. I mean, it's not like most of the lambdas are coming from the jet.
That's, no. Yeah, that is why I ask you. For example, you look at the lambda polarization, which contribute to this the quantity R you are calculating. But how many of the average? How many lambdas you're talking about?
I don't really know that number. But are you saying that it like, if I would go from 0 to 3 GeV, which I guess is here, that most of the lambdas that I'm going to measure in the star detector are jet fragmentation lambdas? Is that right?
No, I'm not making any quantitative claim. I'm only saying there are two origins. And music, if you really had, I don't know what calculation this is, maybe we should, we're getting a little into the weeds here, but if you really do a proper jet propagation calculation with jet fragmentation, it should not be too bad of an estimate. So if that's what you've done, fine. If it needs to account for, the messy hadronic physics of jet fragmentation in addition, that's something that on top. I make no claim that it will make the process disappear. I'm only saying it will be some dilution, maybe mild, maybe negligible, maybe something.
Peter, do lambdas fragmenting from jets get polarized in any plane? I've never seen any.
Yes, they do. Yes, for people, those are leading people have measured leading lambdas, I believe. Not in heavy ions. It's been a project kind of in the back burner for a while that we would like to move to the front burner.
And they're polarized in some
direction. You have an additional vector. So you've got the beam and you've got the jet direction. You actually have a vector with which to measure kind of a spin direction. Yes, there are spin effects in jet fragmentation. Lambdas.
Yeah, I guess. Yeah, I mean, certainly right. So there is no jet fragmentation here at all. This is pure medium. My naive, I guess, but I still don't think it's naive, expectation is that at low PT, the number of lambdas coming from the medium is going to be a lot more than the number of lambdas coming from the jet. Furthermore, we're not looking like along the jet direction, we're looking around it. But yeah, I mean, if there's like 10 times as many lambdas coming from the jet fragmentation as from the QGP, then yeah, I guess that would dilute
I think we got off into a corner here. I think that's, the question is clear and a calculation could illuminate. I think that's
yeah.
fine. I don't think we're actually disagreeing. More questions for Mike?
Yeah, Mike, this is Luciano. I do not know how to raise my hand. So I just wanted to make a comment and not to ask a question, because I mean, given my decrepitude, I get very confused with the indices of all the tensors, so I don't even pretend to get into that. But, you know, as I get older, I tend to dream rather than think. And what I dreamt during your talk, sorry, I was perhaps nodding. So was two things. First of all, I thought about a famous picture of, that was taken with high-speed photography at MIT of an apple which is shot by a projectile. And that would be very much like a central collision of a proton going through some heavy nucleus. And then looking at how the apple falls apart. Given the fact that the analogy to me didn't even appear all that direct, I thought of something else, which actually may photograph events of this sort in a macroscopic way. If I used to shoot at windows with my slingshot when I was a little bit younger, but you can imagine doing this experiment, perhaps with a gun, and you shoot at the window, and you see, or a glass plate, and you see that a pattern of cracks develops, especially at high speed. The number of cracks will be less, and you will find that there are radial cracks which come out from the center where the bullet has hit. And then you're going to have ring cracks, which are going to be very close to one another, parallel to each other, you know, with the center where the bullet cracks. And as you go farther and farther away, the spacing gets bigger. I think that that essentially tells you in a very visual way how the stress on the glass propagates from the center where the collision, primary collision occurs, as it propagates farther and farther away. And by taking the gradient of that, you may get something, you know, like vorticity and whatnot. So I don't have any other insight, but I would perhaps suggest that you might either try, or if not, well, you're down in Rio, are you?
I'm in Campinas, near Sao Paulo.
But there you can just go around shooting just as well as in the United States, right? So you may try and do the experiment, and you will see how indeed the pattern of fractures in the glass will immediately give you an idea on the vorticity on each element, on each fragment of the glass, which is detailed by the cracks. The other thing is that to me, it seems futile to go and look at the spin polarization of a given particle. This is eminently collective, okay? And you're going to get all the best information if you look at the collective behavior of the fragments coming out, and not at the individual polarization or alignment of the spin of a particular particle. That's about all I have in terms of wisdom.
I think that you were dreaming for most of my talk, Luciano.
Really?
Yeah, that was like the whole talk was about.
Mike,
I mean, how do you like
comments?
my dreams?
Mike, did you have any response to Luciano?
Oh, I was just going to, maybe not to the second part, but about the glass. I mean, the thing is, vorticity is manifestly three-dimensional, which is one reason why I think it didn't get maybe the attention it might have deserved early on, where there was a lot of 2+1 hydro going on. So
if I can interrupt you, the glass will tell you what is the three-dimensionality and how you can have locally as a function of radial distance, you know, a curl. And you will see it by the fact that the little quadrilaterals, if you want, that you form as you move away from the center along two radial cracks, you're going to see that the spacing of the equatorial cracks is going to increase. So it means that the tensor quality is indeed predicted because you take the gradient along the radius and you see that the size of the little fragments gets actually bigger as you go away.
I want to see you guys here. Okay, yeah, I mean, I just want to say just about the shooting things and so forth. So one thing that
be careful, eh?
Yeah, well, it's already been done. So they have these shells, these armor-piercing shells that they develop for the military, and they shoot them through iron plates. And early on, and Giorgio knows this, I kind of wanted to involve a discussion of this in the paper, but we cut it out. It's really fascinating. I mean, here we have two objects, a armor-piercing projectile hitting a steel plate, no fluid, okay? But if it's hard enough, they flow. They actually thermalize as they interpenetrate and develop vortical fields. In fact, exactly these vortical fields, toroidal vortices, as they interpenetrate and equilibrate. So, I mean, the idea is like what you're drawing these proton-gold collisions as if it's like already a QGP. Well, it could happen. I mean, if it's an armor-piercing shell and a bullet, it wouldn't be the only time that ever happened, I guess.
I prefer glass than a steel plate because there you have very clear designation of the limiting stress that creates the cracks.
But maybe not a fluid. And this also breaks through and makes the same geometry. But yeah, I mean, glass, at least it stays still, but you can take high-speed footage. You know.
Okay, thanks, John. Any other questions?
Experiment with different velocity.
Yeah, John, let's
velocity,
okay.
And you're going to have an evolving pattern, which is going to be very interesting. Huh?
Thank you, John. Giorgio has a question or comment. Go ahead, Giorgio.
Yeah, I mean, just as a comment, I don't have a question. I agree with everything Mike said. Just as a comment to I think that the question, how many particles make a vortex is an extremely good question, but it's not a question to ask at this seminar because it's a sort of theory question, which to me is still unsolved. It seems that you have fluids with very few particles, like 50 particles. And I do not see a satisfactory answer to this in the theory literature. Most of the literature is on attractors and stuff like this, which is about how come there is hydro in large gradients, but not about how come there is hydro in few particles. I mean, I have some ideas, I've written them down, I have a couple of papers on this, but it seems to be an experimental fact that you have a fluid with very few particles. So do you have vortices with very few particles? That has an experimental answer. And this is the point of this investigation. If you basically see vorticity observables in systems with 50 degrees of freedom, this is something that theorists really need to answer at a fundamental level.
The fact that we describe things with Cooper-Frye really probably means we should make a distinction between particles and fluid. I don't think it's a fluid of little things bumping into each other.
I don't think the quanta and the fluid is countable in QCD. One simply doesn't. You can approximate, but there's no. It's a quantum system with things coming in and out of existence. If it's got a fluid description, I don't think the number of degrees of freedom is precisely quantifiable. More questions, comments?
I don't think
Mike?
you, yeah, let me comment. I don't think you need a fluid to produce vorticity.
True.
Just a few particles, as far as they have some kind of non-vanishing orbital angular momentum with respect to a direction, and that is a vorticity. You know, it can be defined by a few particles. Yeah. So
Yeah.
my concern is not that. My concern is really what is the strength of the signal. You know, you have, after all the background. You have the background from the bulk medium who have collective flow. You have fragments from the jet, and then on top of that, you have these few particles coming from the jet-induced medium response, who happen to have some kind of non-vanishing angular momentum respect to your jet direction. Okay, so this is really experimental problem. You know how, for example, how do you manage to subtract background? And
Okay, I need to stop you because I just need to interrupt that. I mean, I think that lambdas that come like from the jet, fragmentation lambdas, that I agree with you, that's not included, but it's you seem to make a distinction that there's the contribution from the flow and there's the contribution from the response and this is from the medium. That's all in there. I mean, there's not a part of the medium that responds and a part of the medium that doesn't respond or something like that. It's a fluid which has then, been disturbed by this bullet. It's really a bullet that we put in there. And there's not like a responding part of the fluid that we have to subtract from the responding part or something like that. So
I don't. In that case, I don't agree with you, because if you have a flow, just a flowing, expanding QGP,
yeah,
and that does not naturally have any vorticity with respect to some direction, but then you shoot a jet through it, okay, and it's only those medium response part which is get fluid. The rest of the system probably will even not feel the jet.
Yeah, that's all included in the calculation, all of that part. So you asked, is this only the part that's responding, which honestly I still think is an ill-defined question, but just to answer that question, it's all included. Even the part that doesn't feel the jet is included. That's why we get something on the order of, 1% or so. That's in there. What's not in there?
Wow, that's yeah, that's I'm a little bit sort of. I really have to. Maybe we can talk offline and find out what is the numbers coming from that. Yeah.
That sounds good. I mean, I wouldn't even know how to like it's a hydro system. I don't know how to take away the part that's responding. That's not even well defined. But yeah, we can chat about it.
So I think the statement that this is an experimental question, or a question will be answered experimentally, is a good way to end, where we're 10 minutes past, and unless somebody has something super burning, I think
well, the good part is because you get to analyze your own idea.
Yeah, let's hope. We need the data on tape. Yeah.
All right. Good. Okay. Well, thanks, Mike.
Okay. Thank you, everyone. Nice to see you.
Thank you.
Bye-bye.
Yeah, thank you.
Ciao, ciao.
Bye.
Ciao.